Good afternoon, everybody. From my side, I'm a master student writer from Technische University of Darmstadt, from the Measurement and Sensor Technology group of Professor Kupnik. And first, so I present my work on image enhancement and object localization for ultrasonic phase arrays. And first off, let's start off with the current state of ultrasonic phase arrays. So here you can see a spiral type of array, which is capable of producing high quality images already, as you can see here with this picture of a hand. And this has, due to its size, which you can probably estimate from the picture here with the hand, this aims more into industrial applications. But there are also different kinds of arrays, also by our research group. So this array has an aperture size of with the diameter of 4.2 centimeters. And it uses 36 MEMS microphones and one narrowband transducer for the sonar imaging. And for this array, we see the applications especially in mobile robotics as a complement to LiDAR systems, for example, or camera systems. As LiDAR systems have trouble with reflective or translucent surfaces, and camera systems can't really see like harsh environments, like you can see here in smoke or fog conditions. And therefore, I try to get point coordinates out of this, because if you now imagine you're an autonomous robot and you want to maneuver through this group of people, what you really need are point coordinates where not to drive. And yeah, we want to obtain these point coordinates, but it's not what you really directly get out of this type of sonar system. So we use conventional beamforming for the data processing of these microphones here. And what you will get out there is this type of sonar image. And you can see that you have a main lobe, which is surrounded by side lobes. This is because of the characteristic point spread function of the array. And a little disclaimer here. So for the data you see in this talk here, we use simulated data based on the geometry of this array. It's more easy to obtain high quality localizations in combination with these with a high variability in these images in simulations at the current state. And yeah, what we want to get are these reflective positions here, marked in green. And yeah, now I want to tell you, but this is not so easy. As you can see here, one obstacle which works fine, but if you have two near side by side, the main lobes can overlap with each other or with the main lobe of the next reflection. And you have variability in the reflectivity of the objects. So if you have one object with high reflectivity and one very weak, it could be even the case that the side lobe of the strong reflecting object is stronger than the weak reflection. And if you now think of a trivial approach to solve this problem, if you only maybe saw one reflector, you might think, okay, you can simply use thresholding and connect the components, for example, and say, okay, in front of this main lobe here, you got your obstacle. But as you can see with two reflectors or varying reflectivity, this doesn't really work well. Of course, there's more advanced work on this topic. So you have on one hand the deconvolution approaches, which here is as an example the clean algorithm, where you try to deconvolve the image with its point function to get better quality image. And you also have the dictionary approaches, where you have pre-recorded signals, which the belonging point coordinate of the reflector, and then there are different approaches to look up the matching signal, which you have then your incoming signal to get the point coordinates. And these are mainly the two main ways to do this. And we want to do a whole different approach. So we see these images as kind of natural image approach, as you have like a pattern here that you can recognize. So why not use the current advances on natural images to do so? So we found the algorithm of Jose Rivera pretty useful. We use a two-step approach. So in the first step, you have the segmentation, which gives you your area of interest. And in the second step, with the clustering, you can then find the center points of your area of interest. And this is what we will use to get our estimators of the reflective positions out of these CVF images. So let's dive into the algorithm. So the first step will be the segmentation here. So you get your CBF image in and your segmentation out, which gives you then area of interest around the point where your reflector should be somewhere. And we used an auto-encoder type of network based on exception here to do so. And for the clustering afterwards, you also need to estimate how many reflectors do you expect to be in your image. And this is calculated in this parallel path here. And if you now combine the information from the segmentation and the object count in a Gaussian mixture model that we use for the clustering, then you can obtain these red markers here, so the estimated reflector positions out of this segmentation here. And yeah, now I come to the training of the network. So as you can see here, this is the true map, and this is one segmentation. And yeah, for the loss function, as we only have in the ideal case one high value pixel at the real location, the established segmentation loss function doesn't really work that well in this case. So we use here the weighted Hausdorff distance to train the segmentation part, and yeah, the regression part here for the reflector count estimation. The Huber loss I would recommend here, but you could also use your normal mean squared error, for example. And yeah, as I said, we use simulated data, so we can vary the parameters and we randomize as much as possible. But we have some boundary conditions, so we used 30,000 images in this case, and we limited the maximum amount of images here to 6, of reflectors to 6, and the minimum angle between two objects here we limited to 5 degrees, and the weakest main lobe in the image should have at least 50% of the amplitude of the highest main lobe in the image. And yeah, for the evaluation then we used 2,000 images with the same boundary conditions. Here you can see that in 83% of the cases, the reflector count estimation was correct. And out of these 83% of the images, we then calculated the localization performance, as otherwise it wouldn't make any sense because we would mix up two different types of errors. So you can see here the mean angular error is quite nice, but we should improve the standard deviation in the future work. And here you can see the distribution of error, which might be interesting around the angular direction. So you might think, okay, the algorithm doesn't really work well at boundary conditions, at borders of the image, but this is mainly because we don't sample uniformly our images, because then you have the constant width of the point rate function throughout the image, so approximately, and so the resolution here is decreased, and this causes an increase in the error in this part of the image. And yeah, our main achievement here, I would say, is the improvement of resolution. So we were able to differentiate two neighboring objects with distance between them in the angular direction of 2 degrees in the center of the image, of course, because there the resolution is the highest. Even if the network has only seen data where the neighboring objects were at a distance of 5 degrees as a minimum, so we have some generalization already here. And in comparison to the claimed resolution of the original sonar system, which was 14 degrees, we could now, after the clustering process, gain a resolution of 2 degrees. So the 14 degrees were calculated when there were two maxima visible in this function here. And for future work, I want to do a brief introduction. So we try to improve our work, of course, by using more data, as 30,000 images aren't that much. And we want to optimize our hyperparameters. And further on, we think about upsampling here in the upsampling path for the segmentation network, further than the image size, so the input image size, so that we can use sparsely sampled input images and still gain high quality localizations. And afterwards, we will focus on adapting our algorithm to the 3D domain. And of course, most importantly, we finally want to get real-world results on real-world data and compare our segmentation approach, for example, to clean algorithm and or Richardson-Lucy, for example. So finally, I want to thank you for your attention, and my supervisor Gianni Allevato and my professor for the opportunity to present my bachelor thesis to you today. So If any questions, yeah, feel free to ask them now or later on.